Hello and welcome to the 2020 edition of the DFT Summer School. My name is Gregor Schöner. I'll be teaching many of the core courses or core lectures of this summer school, and I'll begin right here with the introduction into the topics of the school from a scientific point of view. So ultimately many of us try to understand how the central nervous system, together with the body immersed in a structured environment, generates behavior and thought, right? That's the global task, perhaps of psychology, of neuroscience, of cognitive science, and so on. Some of us also seek ideas for how to build artificial cognitive systems that may perceive and act and think on their own, and are very often thought of as being human-like or animal-like. Now, much of an organism's behavior, animals' behavior, can be understood in terms of relatively simple and maybe fixed perception action patterns. And so when we think about cognition, we can think about it in a very simple-minded perspective as whatever comes between sensing and motor behavior. And the idea is that would be, now very little comes between those two if it's a fixed action, perception action pattern, while the more invariant that relationship is invariant, for instance, against change sensory input, against delay, so invariant in time, you can act later than when you receive the sensory information, or against changes in exactly how you're bringing about the action through different effector configurations on. So the more invariant, the more cognitive. And similarly, if the ultimate behavior is not really fixed or determined by the proximal stimulus or some inner states, something like knowledge or representation or anything like that matters for how you behave, then we call that cognitive. I just want to be very concrete and simple. And I wanted to say that because of the classical view of cognition. So if you look up in a classical textbook in cognitive psychology what cognition is, then often you find definitions that refer to relatively abstract ways of thinking about it, and I call those computational views. So it emphasizes, that classical definition emphasizes the capacity to generalize, as shown in the abstract invariant nature of the represented objects, and the systematicity or rule-based processes, the capacity to generate many different, often they insist on unboundedly many different actions and thoughts and so on. This runs under the label of productivity, or sometimes as more specific meaning compositionality. So that's a tradition where cognition is thought of as the manipulation of symbols, and these symbols reflect the abstraction that occurs here, abstraction from the sensory surface or the motor surface, for instance. And in that view, of course, entails the problem of instantiating these objects, bringing them out in the first place, the famous grounding problem. Now, that view of cognition is ultimately an information processing view, and it leads to the view of cognition as a computation, or computation ultimately means that you have something that the computation is based on, and then you return the result of that computation, which is what the function evaluation is, mathematically speaking. So, for instance, in the relational cognition domain, which we will be addressing later in this week, you could take an example like the concept of to the right of. Being to the right of is a function that takes as argument the position of the target object and the position of the reference object, and returns an object, returns a truth value or probability of that relationship. Now, that would be some way of formalizing this kind of thinking. And then, of course, very famously, you can nest and concatenate in complicated ways such function calls that would make these cognitive processes so powerful and productive, right? So that's a classical perspective that is still quite prevalent, I would say, even though people maybe no longer defend it in very formal ways. It's still very strongly the intuition that's around. Now, connectionism is looking at the neural basis of cognition, and connectionism I'm arguing is in a first approximation actually not entirely opposite to that view. So the connectionist view of neural function is also strongly based on the input-output picture. So the individual neurons are considered to be input-output threshold elements, and essentially they're summing their inputs, and then a sigmoid threshold function generates the output. And you can chain them up in forward neural networks. And actually, connection neural networks are much richer than just that. Some of those have recurrent loops, but I'm positing here as a sort of a overall assessment that the functional significance of these networks very typically still derives from a output is a function of input characterization, even though there are roles for recurrency in bringing about that functional relationship, and some of those, for instance, entail keeping activation around, like in long short-term memory, to act on that input later. So there are some forms that will come back to that already overlap with what we'll be talking about. But it's still strongly a input-output picture. And so although connectionism is certainly a position taken against symbol manipulation as the core principle, it still has this functional evaluation perspective on cognition, I would say. Could sort of, as a caricature, say black boxes that make input-output computations are replaced by clouds of neural networks that also produce some kind of input-output characterization. So I make this contrast that I'll have to soften later to point to the other view that we're coming from, the view in which cognition emerges in evolution and actually in individual development as well from the sensorimotor domain. So in biology, neuroscience, that's very clear. For instance, if you think of where in evolution did the first forms of memory arise, then you find they arose in the context of spatial navigation, of knowing where you are and how to get somewhere. It's not by chance that cognitive spatial maps are being used to study memory in animals, because that's sort of the most fundamental function of memory. And similarly, decision-making is really anchored evolutionarily in action selection, what to do under certain circumstances. So that is just some two examples, and sort of illustrates that, biologically speaking, cognition has evolved as something that supports action, behavior, survival, right? That's very specific to that. And you see that in the structure of the brain. The brain has evolved in a very great way. If you look at across many different species, and even in a large ensemble like all vertebrates, you find a lot of homology across very different species. For instance, here's an example. Schöner has recently published with a colleague a review of the basal ganglion and its role in action selection from the lamprey to the human, so over 500 million years of evolution, and finds very strong homology, strong invariance of the basic structure of the action system in these brains, in these nervous systems. So one idea coming from that insight that cognition emerges from the sensorimotor domain is that a neural account for cognition is an account that is specific to the repertoire of cognition, of different forms of cognition that has arisen from evolution. So you're looking for a specific theory of the mind, and that would be then also of the brain, of the functional structure of the brain, where there are specific areas and functions dedicated to different forms of perception and motor behavior, and then working off that, rather than some abstract computational machine that could do something very abstract without any grounding in the sensory motor processes. So I want to elaborate a little bit and take here this example with my kids playing soccer when they were small. Sensory motor behavior, I call that here sensory motor cognition, to point out that even simple actions like activities like that, physical activities, entail pretty much everything that we think of in cognitive psychology as cognition. So clearly they have attentional selection and the control of gaze in this case to orient in the world, to collect sensory information from the world. Perception is active sense of looking for things, both physically with the eyes and the head, but also in terms of selection of what you're paying attention to. And this actually entails working memory. You're not actually making a complete visual search every time you look for the ball, right? You have prediction from working memory where the ball is likely to be, and then you have a much more efficient process of finding the ball and other objects. And maybe not unattended objects, like the objects in the background, for instance, might not be in your scene representation because they're relevant to the activity you have right now. Clearly, you have action plans, you make decisions, sensorimotor decisions about next moves and where to look next and so on. And there's a sequence to your actions. And there is goal orientation, both at a very literal sense, orienting to the goal if you're trying to shoot the ball into the goal, and of course also in a larger sense. And good players might have even strategy and planning, and there's actually social interaction, communication, and so on. There is motor knowledge, not just the skill that you have, but also knowledge about the world, about how slippery the ball is, how the ground is, how slippery for your locomotion, and maybe how roughly to tackle and things like that. And there's background knowledge, literally the rules of the game, but then there also that background knowledge of exactly how to, for instance, touch the ball and things like that. So the famous background knowledge of artificial intelligence that I'm mentioning, that is particularly hard to formalize and is important in this domain. That's witnessed by the fact that current robots really suck at soccer and much better at abstract games. Even Go, right? They play very well, but there's no robot currently that plays anywhere near like my kids did, even back then, and not being very good soccer players. And of course, there's learning from experience. You cannot prevent yourself from learning from experience when you do soccer. So there is little in a cognition that isn't reached in a simple case like that. Now, the fact that that form of cognition is really linked to the sensorimotor domain has implications for what properties the underlying processes have to have. So clearly, as motor behaviors, there's some underlying graded state. Motor behavior requires graded states. Perception requires graded states. It's actually continuous time. It's a control system that acts in continuous time. It can be linked continuously or intermittently to the sensorimotor surfaces, so that understanding how discrete events like decisions or changes between different categories of behaviors have to be understood, how they emerge from the underlying continuum. This happens in closed loop, so the world changes as you act, and you're then acting based on that changed world. And I'll argue in a moment that really implies that we have to have dynamic concepts to talk about it. We have to have stability. Every control engineer knows that. Have to have stability, and I'll elaborate on that a little while on. So one could say that the embodiment hypothesis, embodied cognition kind of hypothesis, is the idea that cognition inherits these properties from embodied cognition. This cognition is done in the same style. It has the same properties. It's dynamics rather than function evaluation. And so that is not a view of embodiment in which you say that all cognition entails motor. Some people have said that embodiment is that you always activate the motor system a little bit when you think. And I think that is, it's possible that there are small things like that, but it's not clear that that's really mandatory. So I think of the embodiment hypothesis, even in its radical form, as a much more subtle hypothesis, which really says that cognition has these dynamic properties that come from the sensorimotor domain and have that all the way through. So even as you move to really higher cognition in which you do not need to, and maybe not typically activate motor systems, even there is no boundary beyond which these sensorimotor principles, these properties inherited from the sensorimotor domain, no longer play a role. And that's very much the perspective that we will be using when we talk about neurodynamics in this summer school, and that we're buying into when we're using dynamical field theory. Now, I use the word dynamics, and I'm not sure if everyone knows what that's supposed to mean, and so I want to introduce this notion a little bit more conceptually here in a few slides. And I do that in reference to the Braitenberg vehicle metaphor. I'm not sure everyone knows Valentino Braitenberg, a neuroanatomist who used this metaphor to illustrate principles of the nervous system. I'm going to use a very simple example from his work. He used this as a teaching device, and that's how I'll do that here too. So he talked about vehicles as a metaphor for organisms because organisms would be characterized by the carrying their sensors and the motor systems through the environment with their body. So it has this notion that the sensors moves when the actuator brings something about, just like in a vehicle. We'll later see it's a bit different from an arm, a robotic arm, where the sensor might not be on the arm. Now, when you in this simplest example, the sensors are connected to the motors physically by being connected to the same body, and in terms of a nervous system, the nervous system transports some inner variable, the activation variable, from the sensors to the motors. So the sensor here is a transducer of some physical quantity, some physical intensity to this inner activation variable, and the motor is the reverse transformation, takes activation and then generates some physical activity. So when a system like that has these four components, sensors, motors, body, and nervous system, is embedded in a structured environment where whatever the sensors are sensitive to, the intensity is distributed in some way that is on the right scale for this organism, then meaningful behavior can emerge. In this example, this is the so-called taxis orientation system. It has this nervous system that is feed forward and unilateral, and with the inverse characteristic here for the sensor. So what happens if you have a larger sensory signal here at this sensor that's closer to the source, you would be here at that higher level of intensity, return a lower level of activation. A lower level of activation would generate a small amount of wheel motion at that left wheel. So this wheel turns more than that wheel, and if you have a vehicle like that, that would mean it would be turning toward the source. As it approaches the source, if the source is a high intensity source, activation would go very low, and both motors might turn very slowly. So it might end up actually stopping in front of the source, oriented to the source. Right? That's sort of a mental simulation of what would happen if that system was in that environment. And so what I'll argue now is that behavior emerges as a stable solution, an attractor solution of a dynamical system. So the dynamical system is sketched here. It's a system that has the orientation of the vehicle in the world. When the vehicle moves, that's the heading direction. So some angle against some axis that says where the vehicle is currently headed. And on this axis, I have the turning rate of the vehicle. I'm neglecting here the forward motion. I'm just thinking of how strongly it turns. And the turning rate is really the derivative of the heading direction, right? It's the rate of change of heading direction. That's the turning rate. And that is what makes the dynamical system, that you have a certain state variable on one axis here, and you have its temporal derivative on the other axis. That makes it a dynamic system, because what that means is that some initial value for the state variable, like some heading here, this function returns the rate of change. So the rate of change here would be, for instance, negative, and that tells you in which direction that current state is going to change. So for instance, this arrow here indicates that you're going to turn, go to smaller heading directions, turn to the left, let's say, depending on how we define the angles. You could, again, do sort of a mental simulation, which would essentially be like integrating that equation in your mind and saying, well, next moment in time, I'll be maybe at this heading and have an even still negative but a little smaller turning rate, and so on, and continue until you end up here in this so-called fixed point. The fixed point is defined by having a zero rate of change, so no more turning. In other words, when you have that heading, you're going to go straight from then on. You're not turning anymore. And because you're attracted from this side here to this fixed point, we call that an attractor. It's actually what is defined as stability. I haven't actually explained yet that you're also attracted from the other side, because if you have a heading that is smaller than that heading of the at the attractor, then you have a positive turning rate. So when you increase your heading, you can see you really converge to the heading, right? So that's the key notion of a dynamical system with an attractor. The attractors that we'll be talking about are always fixed points, so zero crossings of the turning rate, and the negative slope of the dynamic. We call this rate of change function as a function of the state variable dynamic. This dynamic here, the negative slope, that marks them as stable states or attractors. And you can see it's intuitive. If you have that negative state, then this kind of mental simulation that I just went through works. Now, I'm just claiming that that's the case. I want to briefly derive, in a sense, that fact by going through the characterization of the vehicle and then showing you that this dynamic actually emerges from that. So let's first look at here this leftmost sensor that's connected to the leftmost motor in a purely feed-forward way. The nervous system is really just transducing the activation the sensor generates to the motor. So it's an input-output description because it's a feed-forward neural network. And you can do that very easily by just concatenating the sensor characteristic and the motor characteristic, right? The sensor characteristic goes to the activation variable goes to the wheel motion, so I can eliminate activation by concatenation and just look at the function that returns wheel motion as a function of intensity. So if you're familiar with concatenation, you know exactly what I'm talking about. If not, you can think through this, high intensity, low activation, low wheel motion, so it's got to be small here. And let's say low intensity, high activation, high wheel motion, so it's going to be large here. And if you, more globally, if you have a positive function, monotonic function, it's not going to change anything. So if you concatenate these, you get the negative one. No. So very intuitive that will be for one side the input-output function, right? That's the input, that's the output of that subunit. If you think of the two subunits, you can characterize both of those by these forms of functions. And if I'm now interested only in the difference in the turning rates of the wheel will be the turning rate of the vehicle, right? If you have two wheels that turn different amounts in a vehicle, usually it would be a round robot, and the wheels are in the center, and I just drew it like that, like Valentin did, just to make it, look more like a vehicle, I guess. The difference in turning rate determines how the vehicle rotates on the spot. So I can easily derive that input-output function of the complete nervous system by just taking the difference between these two curves, and that returns simply a function just like that. You can see that, for instance, by writing down the formula where the turning rate on the left is some constant here, the offset minus the intensity, and the same for the right. And if you take the difference, then you get just the difference in turning rate of the wheels on the left and the difference in input on the right with a negative slope. And that's what we're seeing here. So that's the characterization of the two feed-forward paths here. Now, to understand what that does to the vehicle, we'll have to look at the source of intensity, and for that we have to have a model of the environment. That's actually the part that's very much overlooked in much of neuroscience, right? It's not enough to just specify the stimulus. To understand how behavior emerges, you have to have a model of the world. So here, let's say a very simple model would be that if there's a source somewhere in the environment at some heading, then there is some, let's say, monomodal distribution of such intensity, and the two sensors can be thought of as measuring the difference in intensity between the two locations. You can think of that as being because they are slightly different distances from the source and the intensity falls off with distance, or because, let's say, these sensors have some angular characteristic. It doesn't really matter the details, but in any case, you can see that the difference left minus right is sort of a measurement, a difference measurement of intensity. And so it would be, if you take left minus right, it would be negative difference here on the left up to here, negative difference, and then would be positive difference here on the right, and that would be sort of like taking the derivative of that curve, right? So the differences in intensity left right as a function of heading make this particular function. And now all we need to do is concatenate again these functions. So here we have the function that links heading direction to difference in sensory information left minus right. This is how we characterize the nervous system, which takes as argument that difference sensory left right and returns the motor left right. Concatenate that, you can get rid of this inner variable, which is the difference in intensity left right. And you know what will happen if you have that function and you concatenate it with a negative linear function, then you're going to get just the flipped function. The flipped function is here. And so on the right axis with the heading direction, on the left we have the difference in the turning rate of the left and right wheel, and I argued that is actually the turning rate of the vehicle. And there you have it. That's the dynamics I was talking about, and this zero crossing is where the source lie, where the local maximum here, where the local maximum of the intensity distribution was. So that's that little derivation for the dynamical system. So interesting to see, you have a feed-forward neural network, purely feed-forward, right? This would be an input-output kind of network. But if you link it to an organism, a body that's in the world, and that is to which the world is in closed loop, then you get a dynamical system. We call that a behavioral dynamical system. Behavioral because it is its state here, the state variable, is a physical variable that characterizes the state of the system in the world. It's not a neural variable. This view is familiar, perhaps for many of you, from cybernetics control theory, and there would be a cybernetic interpretation of the dynamics, which would typically say that the central nervous system reduces the deviation of the desired of behavior from the desired behavior to zero. Right? That's sort of roughly what cybernetic thinking is like. And you can think of the desired heading as this, and then this distance here from the desired heading is reduced to zero by the dynamics, right? More specifically, you would say the sensors measure something like an error, and the CNS then sends a feedback control system to the actuators to reduce that error. So for instance, if you think back of that signal, you can think of the delta I, the intensity difference is the error, in the sense that when you're right on the source, you would have the same intensity on the left and the right. So you want to reduce that error to zero. And the control signal is would be a P controller, in sense a negative control signal that's proportional to that error to the motors, right? That would be sort of cybernetic thinking for those of you who know that. So here you would call that the control signal, and this here the error. Now, I already mentioned it's closed loop. It's and you see here in the cybernetic formulation, it's very clear that it's only because you're in closed loop that this works. And the closed loop really means that the sensors receive the sensor information that is caused by the action of the vehicle. Right? If the source is stationary in the world, the only reason why you see different intensities on the two sensors is because you acted, and the action is brought about by the physical state of the vehicle. So it's the heading direction, and heading direction being a velocity type variable, so you're really moving in the world. That view, the cybernetic view, is a special case, is a limit case, and it doesn't reach all properties that we want. So when we're talking about dynamics, we're talking about something broader than that. So for instance, it does presume that there is a single goal, a set point that you're wanting to get to. And here is an example where you can see that that's not as general as dynamics is. For instance, if I have two sources in the environment that create a bimodal distribution of intensity, then you can see by the very similar logic, it will generate a dynamics of the vehicle where the turning rate as a function of heading has two attractors, two zero crossings with negative slope, actually separated by a repeller, a fixed point that has a positive slope. Is not stable, it's actually unstable. And essentially, if you're to the right of this repeller, you're going to converge on this source. If you're on the left, you're going to converge on that source. So you're making a selection decision based on your initial heading. And that's actually a nonlinear dynamics, right? A very strongly nonlinear dynamics that is a typo here, that generates decision making. We'll see that in the course So that limitation has a lot of implications, more than one might first think. So for instance, it has implications for the nature of the perceptual variables, which are not just error signals, because error signals always refer to something where you know what the zero error case is. So you have a unique target sensory signal, right? And well, perception is a much more general phenomenon where there could be different perceptual outcomes. And very similarly for the state variables. So they're not just error correcting control signals. They are actually signals that can generate multiple different behaviors. So dynamics in our sense is not the same as cybernetic control theory. One could rather say the cybernetic point of view is like a special case of what we'll be talking about. So why is it so important to have stability? You will see this in the course that will talk about stability a lot. It will always be important. So one idea is already evident from the example I gave, the Braitenberg example. Stability is sufficient in the sense that if you arrange for the behavioral variables that generate movement to have a stable stability property, so to be an attractor, then the behavior comes about just by that. You don't have to tell the system in detail what to do. It just follows the dynamic to go to a stable state. So it's sufficient. It's also necessary. That is, if you don't have stability, then in general you will not get the behavior. It's not the correct behavior, you get some behavior. So I take an old example that actually was a critical point in the development of these kind of ideas. Work I was involved in with it by Scott Kelso, where he found that coordination patterns have stability properties. So this is the study of relative timing, relative phase of rhythmic movements, with finger movements at the time, and you find that you have essentially two patterns, and there's a loss of stability of one of those patterns. So here's an example. So if you do an alternation pattern where one finger moves in the opposite direction and then the other finger, so anti-phase, and you speed up the motion, different metronome settings, then you find at some point you can't really sustain that anymore and you switch to in-phase. You can all try that at home. And one can estimate the relative timing by something like relative phase and make a lot of analysis of that. And what was found then was that there is a loss of stability that is indicators of the stability of the state. And over the course you will become familiar with those. One indicator is, for instance, the variability of that measure, standard deviation of relative phase in time, as a function of frequency. This is the in-phase pattern, that's the anti-phase pattern. And you see that before you switch, you're switching here and between these two frequency domains. Before you switch, you actually get an increase in fluctuations in variance, and that's an indicator of loss of stability. And a more direct measure is relaxation time. So what happened here is that participants had their fingers mounted in a little manipulandum, and you were able to insert torques onto that manipulandum so as to move the fingers around. And through that, you were able to perturb them away from the coordination pattern they were trying to do. When you do that in phase, they recover within about 400 milliseconds across different frequencies. They recover the correct phase relationship. When you do that in anti-phase, before the switch, so before this point here, you see this increase in relaxation time. So it takes longer and longer for them to recover after a perturbation like that. So so what you see here is that loss of stability leads to switch. When you lose stability, then you ultimately lose the pattern, right? So that showed that stability is both necessary and sufficient for the emergence of coordination patterns. And that will be a major role in the course. We'll always talk about stability and then the loss of stability, which we'll call instability or bifurcation. That will lead to switch, to change of pattern, or change, and later we'll see a change of cognitive function. Now, this was behavioral dynamics, so outer loops through the world. What about internal loops, internal to the nervous system? So like if this is a neuron, a recursive kind of connection like that. So conceptually, internal loops are very important as we are trying to move beyond a pure input-output picture, because the internal state can actually make that the input-output function is modulated, is changed, and it makes it possible, and that will be important for us, that neural activation arises without input or persists without input. And that will be critical to understand, for instance, how you generate movements, how you have working memory, or how you spontaneously, autonomously generate sequences of different actions, not just triggered by input, maybe triggered internally by your nervous system itself. And that all relies on these kind of internal loops. That's why important. Now, when you think of internal loops in neural networks, that's recurrence. And then important point is to realize that when you talk about neural network, as soon as you have recurrence, you need the notion of time. Because recurrence really destroys the function evaluation view of neural networks. You can't say the output is a function of the input, because one part of the input is another output. So without knowing the output, you can't compute the output. And the resolution of that is to say, well, the output that serves as an input at a particular time comes from an earlier time, and then you're computing the next output from the input that was provided by the just previous output. That's how it's done in a lot of connectionist neural networks. Now, of course, in the nervous system, there is no discrete clock like that. And if you think that spikes are discrete events in time, they are not like that. They are not clock-like. We say they are asynchronous, so they just sample continuous time. So we'll need to think about how to do that in continuous time. And the answer to that is, in continuous time, you have dynamics in the same sense I just talked about, a differential equation where some state variable, and I'll call that u now, that's some activation state, is connected to its rate of change, and that forms a function. And this is the generic function formed here, which has a minus u term that makes a negative slope, and you already understand the negative slope is going to make stability. So it's going to make fixed points that will be attractors. So for instance, without input, it will be at that resting level, the attractor. U dot equals 0 would be the fixed point. If this is a 0 here, you put the u to the other side, u equals resting level if there's no input. So you understand why the fixed point is here at that state, and the negative slope says it's a stable state. And then inputs, the conventional way of thinking about neural networks, of course, you add inputs on the right-hand side. And here you see you don't add them directly to activation, you add them to the rate of change of activation. So in the dynamical picture, this amounts to shifting up this minus u term, and that will shift where the attractor is. And for instance, it could be shifted to the right half of this plane, and that where with this positive activation, we'll call that an activated state. So analogous, but now it's an inner variable, activation variable. We'll get a lot more. We'll see about where the minus u term comes from when I just talk more formally about neural dynamics. So why is stability important in neural dynamics? I'll talk a lot about how it's efficient. I'll show you how you get behavior and simple cognitive functions out of such neural dynamics. And then we'll also actually talk about instabilities that demarcate different cognitive functions. So a very similar argument can be made for that, but one can also argue a little bit more intuitively. Stability is resistance to change under perturbation, under a slight change of conditions or inputs or stimulus and so on. And what that concretely means, if you think of cognitive functions, is somehow there are inputs that are distractor inputs, things that if you were to react to as a nervous system, then you would not actually do what you're currently trying to do. And so you want to resist reacting to those, and that means you have to make a selection decision. So for instance, if I have these two sources and I have some neural activation field, we'll introduce these kind of notions so that there's a peak over one location where that source is, and a other input at the other location is being suppressed. We'll see how that works. Then you could say the source 2 is now distractor input, and you don't want to switch your decision to that distractor input. So that could be a reason why you really need to have stability to be able to resist such distractor inputs. And one could make the argument that the dense connectivity that characterizes the nervous system means that in any given neural state, there are a lot of cables converging on a neuron you're looking at, that for that particular function you're currently in is distractor input that you must resist to stay on target. And you have an intuition for that if you like cognitive control, that you have to stay on task, or that you have to try to pay attention, not be distracted, and so on. So, could argue intuitively that stability is very important in order to create coherent mental states, just like stability of behavioral dynamics is important to create coherent, persistent physical action. So I'll end this introduction by clarifying that the way we use neural dynamics in dynamic field theory is actually as a subset of neural network theory, of general neural networks. So there's a lot of different neural networks, a lot of different mechanisms, and we're not actually claiming that we do something that goes outside that theoretical framework. Actually, rather saying the opposite, we're looking at a much more constrained subset of those networks. We'll say many of these networks are actually not good descriptions of what nervous systems do. And we'll look at the subset that has additional properties, constraints. It has such stability properties. Later we'll see it has the property of having primarily low-dimensional representations, localist, we'll say. They have interaction functions that are in some sense regular and very homogeneous. They have particular instabilities. They have particular solutions active transients, which we'll be looking at. And this course will be largely about these constraints and their behavioral significance. And then, of course, we'll also illustrate all of those theoretical ideas in a lot of case studies, use cases, and so on of dynamical field theory. So this much about the introduction. We'll dive right into the foundations in the next lecture. Thank you.